Welcome to the Deep Dive, the show where we really try to cut through all the noise and get straight to the insights that matter. We're living in a world that's just overflowing with data, right? But how do we actually know that the information we're basing decisions on is, well, truly solid, dependable, robust? It's a massive question, especially when you're trying to navigate these really complex relationships between variables, things that aren't always easy to measure directly. Concepts like customer satisfaction or brand trust. You can't just put a ruler on those, can you?
Exactly. You can't. And that's precisely where this powerful tool comes in, one that's become really widely adopted. Partial least squares structural equation modeling, or PLS-SEM.
PLS-SEM.
Okay. Yeah. It's essentially a method that helps researchers analyze these intricate webs of relationships. You've got your observed data points, the things we can actually measure, like survey responses or sales figures, and then these deeper, often unobservable, latent variables, like the trust or satisfaction you mentioned.
So it's kind of like mapping out a hidden network.
Yeah, that's a great way to put it. Mapping a network where some of the most important players, those latent variables, are kind of hidden from direct view.
And it seems like it's used everywhere.
Oh, absolutely. PLS-SEM is a real workhorse. Research has shown its incredible reach across, well, a whole array of fields. You see it in social sciences, hospitality, marketing, tourism.
Okay.
But its utility goes even further. It pops up in engineering, medicine, even psychology.
Wow. So what makes it so popular, so adaptable?
Well, there are a few key reasons. First, it can handle quite complex models even when you don't have a massive amount of data, which is often a reality for researchers.
Right. Data can be hard to come by.
Exactly.
Yeah.
It's also really good for estimating certain types of measurement models. We call them formatively specified models, where the indicators cause the latent variable rather than the other way around. And it gives you really clear determinate scores for those latent variables. But maybe most crucially, it helps bridge that gap between just academic explanation, understanding why something happens, and practical prediction.
The prediction part.
Yeah.
That's huge for real-world use.
Absolutely invaluable, especially when you're trying to derive actionable managerial implications. It's about not just understanding the past, but getting a glimpse into what might happen next.
Okay, that makes sense. It's powerful.
Extremely powerful. And building right on that point, because it has such reach and influence, it really highlights why ensuring the results we get from PLS-SE are sound is just so critical.
Because if we're using it to make big decisions.
Precisely. If we're relying on this tool to inform decisions across so many vital sectors, business, healthcare, policy, we absolutely need to trust those insights. And that brings us squarely to our mission for this deep dive today. The crucial need for what we call robustness checks.
Robustness checks. Okay. Sounds important. Like kicking the tires.
Kind of, yeah. But maybe a bit more involved. You see, the fundamental problem is this. PLS-SE, at its core, is a sophisticated type of regression analysis. But researchers often overlook these critical robustness assessments.
Really? Even though it's regression-based?
Surprisingly often, yes. Recent research pointed this out quite clearly. And our sources show that while methodologists have made significant strides in developing these complementary checking methods, the actual adoption of these methods has been, well, disappointingly slow, especially in certain fields like tourism, for example.
So it's like having this amazing tool, but not always using its safety features.
That's a perfect analogy. It's like having a high-performance car, but forgetting to check the tire pressure or the brakes before a big race. So today, we're here to understand these critical safety checks, these robustness checks that validate PLS-SEM findings. They're what can transform potentially interesting research into truly trustworthy, actionable knowledge.
Okay. Building confidence in the result.
Exactly. Moving them from just educated guesses to properly tested insights.
All right, let's unpack this then. Our goal today is to get a handle on 3 major areas where research results can be pretty vulnerable if they're not properly checked. And honestly, these are areas where a lot of studies, maybe unintentionally, can stumble. We're talking about nonlinear effects, endogeneity, and unobserved heterogeneity.
The big 3 troublemakers.
Right. So we're going to break down what each of these actually means. In plain English, hopefully. We'll talk about why each one matters so much for the validity of your findings. Like, what are the real-world stakes if you miss them?
Yeah, the so what factor.
Exactly. And then we'll walk through how researchers actually go about addressing them. And to wrap it all up, we'll look at a real-world example to see how all these concepts play out in practice. Sound good?
Sounds perfect. Let's dive in.
1-1, the foundation of trust. Why robustness checks are non-negotiable in PLS-SEM.
Okay, so we've established how valuable PLSS is, especially its knack for testing hypothesized relationships with that prediction focus. It really helps bridge that gap between just explaining things and actually being able to predict what might happen.
Right, moving beyond just theory. But, like any powerful tool, it's not without its challenges. Even with all its strengths, research has identified these, well, blind spots within PLS-SEM. Methodologists have been working hard to fill those gaps, which is precisely where these robustness checks become absolutely essential.
They're our way of making sure we're not just seeing what we want to see or what the simplest model shows us, but what's actually going on underneath the surface.
So what is this fundamental idea of robustness then? What does it really mean in this context?
That's a great question. Fundamentally, robustness is about stability. Imagine you've built this model, this argument, based on your data. Robustness checks are essentially putting that argument through a series of stress tests.
Stress tests, okay.
Yeah. So more technically, robustness checks look at how your core findings, those key relationships, the regression coefficients, behave when you tweak the model specification a bit. Maybe add another variable. Maybe you remove one that might not be essential.
So does the main conclusion still hold up?
Exactly. Does your core findings say that X significantly influences Y stay pretty much the same even when you make these reasonable changes? Does the house still stand firm if you, say, add a window or change the furniture?
And what happens if we skip these checks? What's the risk?
The risk is substantial, honestly. Ignoring potential issues like the ones we mentioned, nonlinearities, endogeneity, unobserved heterogeneity, can pose really serious threats to the validity of your results.
Serious how? Like just less precise or?
Potentially much worse than that. It could mean your conclusions are fundamentally flawed.
Yeah.
You might underestimate a true relationship, making a strong effect look weak or even disappear entirely.
So you might miss something important.
Definitely. Or, conversely, you might find a significant effect that isn't actually real, what we call a spurious relationship. Think about the implications. Spending months, maybe years, on a study only to realize the core finding might be completely off because you missed a hidden curve or an unmeasured factor influencing everything.
Yeah, that would be devastating.
It's not just bad science. It can lead to really poor decisions based on faulty insights. One researcher put it very bluntly, saying these issues must be urgently addressed and reported in the results of PLS, MATO-AC. It's not optional.
So it's not just an academic nicety, it's fundamental.
Absolutely. It's the difference between a finding that's just, there in the output and an insight you can genuinely trust and act upon.
Okay. So for anyone listening, whether they're doing research or consuming it, the message is clear. Don't just take the first model you see at face value.
Right. You need to ask, has it been tested? Has its strength been challenged?
It's like checking the foundations of a building, not just admiring the paint job.
Perfect analogy.
Yeah.
And speaking of foundations, one of the most common assumptions we build these models on is that relationships are always simple, straight lines.
Yeah.
But is that really how the world works?
Probably not always. Let's start there.
Let's do it.
2. Beyond straight lines. The reality of nonlinear effects. So when researchers estimate these path models, those diagrams showing how, say, trust influences attitude, the default setting almost always is to assume the relationship is linear.
The straight line.
Yeah, think of a simple graph. As one thing goes up by 1 unit, the other thing consistently goes up or down by a fixed amount. It's neat, it's tidy, easy to understand and model.
Very convenient.
But as researchers have pointed out, reality is often, messier, more nuanced, and definitely more interesting than just a straight line.
Curves happen.
Curves definitely happen. And the consequences of just assuming linearity when the relationship is actually curved, they can be pretty significant, right?
Oh, absolutely. If you mistakenly assume a relationship is linear when it's not, you're likely to underestimate the true strength of that relationship.
Underestimate. How so?
Well, imagine the effect starts small, then gets much stronger, then levels off like an S-curve. If you just fit a straight line through that, the line will be much flatter than the steepest part of the curve. You'll miss the real action.
Ah, I see. So the effect might even look weak or non-significant overall.
Exactly. Even if it's very strong in a particular range, think about, say, advertising spend and sales. Maybe a little spending does nothing. Moderate spending has a huge impact, but then spending even more gives diminishing returns. A straight line model would completely miss that sweet spot and might lead you to conclude advertising isn't very effective.
Which could be a terrible business decision.
Potentially disastrous. And this isn't just a theoretical worry. I was genuinely shocked when I saw this statistic from a review of hundreds of PLS-SEM studies in tourism and hospitality.
What did it find?
Out of 375 studies, guess how many actually tested for nonlinear effects?
Maybe 50.
Try 9.
9 out of 375. That's tiny.
It's about 2.4%, just 9 actually estimated nonlinear effects. Another 3 maybe mentioned it as a limitation. That suggests a massive potential blind spot across a whole body of research, a lot of potentially missed insights.
Wow. But when researchers do look for these curves, what do they find? Does it change the story?
Often, yes. It can reveal really fascinating dynamics. For instance, studies have found nonlinearities in how tourism resources relate to competitiveness more isn't always linearly better. There can be diminishing returns.
Okay.
Others looked at things like hotel staff turnover. Some factors might push turnover up steadily, but others might have a more complex relationship, maybe U-shaped, where moderate levels of something are okay, but too little or too much is bad.
Interesting.
Yeah, or customer brand equity in hotels, even the link between museum funding and creativity, it shows up in lots of places. The real world often isn't linear, and our models need to be able to capture that complexity.
Okay, so if these curves are potentially lurking everywhere, how do we actually find them and model them within PLS-SEM?
Great question. We need systematic ways to detect and model them. The key thing to remember about nonlinear effects is that the size of the effect doesn't just depend on how much the predictor changes, but also on the level or value of that predictor.
So the impact changes depending on where you are on the curve.
Precisely. Like watering a plant, a little water helps more, but eventually, too much water hurts. The effect changes. It's nonlinear.
Right. So what are the methods?
Well, one common and quite useful method is Ramsey's reset test. Reset stands for Regression Equation Specification Error Test.
Okay, reset test. What does it do?
Its main job is to check for specification errors in your regression model. Basically, it asks, if we add powers of the model's predicted values, like the squared or cubed predictions, does that significantly improve the model? If it does, it's a strong hint that your simple linear model is missing something, often a nonlinearity.
How do you use it with PLS-SEM?
You first run your standard PLS-SEM model. Then you take the scores it generates for your latent variables, those numerical values representing trust, attitude, etc., and you feed those scores into the reset test procedure in standard statistical software like SPSS or Stata.
And if the test is significant?
It tells you, warning, your linear assumption might be wrong here. You should probably investigate nonlinear effects more closely. It typically checks for quadratic, squared, and cubed terms by default.
Okay, so that's one way to get a warning sign. Is there a way to model the curve more directly?
Yes, absolutely. The second main approach is to add quadratic terms directly into your PLS path model.
Quadratic term.
Yeah.
Like squaring the variable.
Exactly. It's similar to adding an interaction term, but here the variable interacts with itself. So if you have predictor x influencing outcome y, you'd add an x squared xx term also pointing to y.
Now, how do you interpret that x squared term?
It's actually quite intuitive. If that quadratic term is significant and positive, it means the effect of x on y gets stronger as x gets larger. The curve is bending upwards.
Accelerating effect.
Right. If the quadratic term is significant and negative, it means the effect of x on y weakens as x gets larger. The curve is bending downwards, maybe leveling off or even reversing, diminishing returns.
And if it's not significant?
Then it supports the idea that a linear effect is good enough. Your initial straight line assumption holds up for that relationship. So these two methods, reset and adding quadratic terms, give you powerful tools to look beyond simple lines and capture the richer, curved realities that often exist.
Got it. So spotting those hidden curves is crucial. But sometimes the issue isn't the shape of the line. It's more like there's something else messing with the line entirely, something external.
You're leading right into our next big topic, endogeneity, the hidden corruptor, as some call it.
The hidden corruptor, unpacking endogeneity. Okay, let's try and unpack this one. Endogeneity. It sounds complicated. What exactly is it, and why is it such a threat?
It does sound technical, but the core idea isn't too bad. Endogeneity happens when your predictor variable, the thing you think is causing an effect, is correlated with the error term of the outcome variable it's trying to predict.
Correlated with the error term. What does that mean?
Okay, think of the error term as everything else that influences the outcome variable that your model doesn't explicitly include. It's the leftover unexplained variation, the statistical noise.
Right, the stuff we didn't account for.
Exactly. Now, if your predictor variable is somehow tangled up or correlated with that leftover noise, you have endogeneity. It blurs the lines. You can't cleanly isolate the true effect of your predictor because it's mixed up with all that other unexplained stuff.
Like trying to hear one voice in a noisy room, and that voice is somehow connected to the noise itself.
That's a fantastic analogy, yes. It makes it really hard to figure out what the voice alone is actually saying.
So what causes this tangling up? Where does endogeneity usually come from?
The most common culprit by far is omitted constructs or omitted variables.
Things you left out of the model.
Precisely. Variables that you haven't included, but, and this is the crucial part, they are correlated with both your predictor variable and your outcome variable.
So a missing link that connects both ends.
Exactly. Let's say you're modeling A causes B, but there's this other factor, C, that you forgot to include. If C influences both A and B, then its effect gets pushed into the error term of B. And because C also influences A now looks like it's correlated with the error term of B, even though the real issue is the missing C.
Okay, that makes sense. Can you give a more concrete example?
Sure. Let's use the example from the source about visitor satisfaction and spending. Imagine you're studying how satisfied visitors are overall affects how much they spend at, say, a tourist attraction.
Okay. Higher satisfaction, more spending, presumably.
You'd think so. But maybe you only measured overall satisfaction. What if you omitted specific aspects like satisfaction with the food quality, or the cleanliness of the restrooms, or the friendliness of the staff?
Right. Satisfaction has many facets.
Exactly. Now imagine cleanliness is something you omitted. If cleanliness is correlated with your measure of overall satisfaction, cleaner places tend to make people more satisfied overall. And cleanliness is also directly correlated with spending. Maybe people stay longer and spend more if the place is clean. Then you have endogeneity.
Because the omitted cleanliness is linked to both the predictor, overall satisfaction, and the outcome, spending.
Bingo. The effect you're measuring for overall satisfaction on spending might be artificially inflated or deflated because it's secretly picking up some of the effect of cleanliness that you didn't account for. Your estimate for satisfaction's impact is biased.
Biased. Okay, so if we ignore this, what's the actual damage? How bad is bias?
It's pretty bad from a research perspective. When endogeneity is present, it violates a really fundamental assumption of regression analysis, basically, that the predictor and the error term are uncorrelated.
And when that assumption is broken?
The consequence is biased coefficient estimates. The numbers you get telling you how strong the relationship is are simply wrong. They become, as some researchers put it, causally uninterpretable.
Meaning you can't say X causes Y anymore.
Not reliably, no. You might conclude there's a causal link when there isn't, a false positive or type I error, or you might miss a real causal link because it's being obscured, a false negative or type 2 error. You fundamentally misunderstand the relationship.
Which could lead to really bad decisions if you're relying on that research.
Absolutely. Investing in the wrong strategy, missing a crucial lever, the practical consequences can be significant.
And yet, you said earlier this is often overlooked.
Shockingly so, especially in some fields using PLS-SEM, that review of tourism and hospitality papers. Out of 375, only one even mentioned endogeneity, and that one addressed it in the study design, not using specific analytical checks within PLS-SEM itself.
Wow, why is it missed so often? Is it just hard to detect?
Part of it might be lack of awareness, and part of it is that the specific techniques for systematically tackling endogeneity within the PLS-SEM framework are relatively recent developments. Methodologists have only really started formalizing these procedures in the last decade or so.
Okay, so the tools are newer. What are those tools? How do researchers identify and, crucially, treat endogeneity if they suspect it?
Well, there's a systematic procedure that's gained traction, developed by Holt and colleagues, which builds on an approach called the Gaussian copula method by Park and Gupta. It's quite clever.
Gaussian copula.
Yeah.
Okay. How does it work? Break it down for us.
Sure. It's essentially a 3-step process. Step 1 is a prerequisite check. Before you even start the main detection, you need to check if the variables you suspect are endogenous are non-normally distributed.
Non-normally distributed, meaning the data isn't a perfect bell curve.
Exactly. The Gaussian copula method works best for detecting these subtle correlations when the data has some skewness or other deviations from normality. If your data is perfectly normal, this specific method might not be the most powerful. You'd check this using standard tests, like the Kolmogorov-Smirnov test.
Okay, so check for non-normality first. What's step 2?
Step 2 is detection. Assuming your data meets the non-normality prerequisite, you apply the Gaussian copula approach. What this does is it directly models the correlation between your potentially problematic predictor variable and the error term of the dependent variable. Think of it as putting that potential secret chat under a statistical microscope.
And what are you looking for?
You're looking for a copula term that the analysis generates. If this copula term is statistically significant, that's your red flag. It tells you, yes, endogeneity is present. Your predictor is correlated with the error term. Houston, we have a problem.
Okay, so you've detected it. Now what? Step 3.
Step 3 is treatment. If endogeneity is detected, the standard approach is to use instrumental variables, or IVs.
Instrumental variables, what are those?
Finding good IVs can be tricky, but the idea is this. An instrumental variable is another variable that has two specific properties. First, it must be highly correlated with your problematic predictor variable, the endogenous one, so it's related to the predictor.
Okay.
Second, and this is absolutely critical, it must be uncorrelated with the error term of the outcome variable. It can't have its own secret chat with the noise.
So it's related to the bad predictor, but not related to the outcome's unexplained part.
Exactly. Think of it as a clean, unbiased substitute that's linked to your problematic predictor, but isn't contaminated by the same issues affecting the outcome. By using these IVs in the analysis, you can essentially filter out the bias caused by endogeneity and get a more accurate, causally interpretable estimate of your predictor's true effect.
That sounds powerful, but maybe hard to find those perfect IVs.
It can be challenging, yes. Choosing appropriate instrumental variables requires strong theory and careful justification. But this systematic procedure, check prerequisites, detect with copulas, treat with IVs, provides a clear pathway for tackling endogeneity in PLS-SEM.
Got it. So endogeneity is this subtle but really potent threat. Knowing how to look for it and deal with it is crucial for trustworthy results. But sometimes the issue isn't an external factor messing things up or a hidden curve. Sometimes the problem is that the average story your data tells is just wrong because your data is actually made up of different groups behaving differently.
Precisely. Which brings us to our third potential troublemaker, unobserved heterogeneity.
4, the many voices. Uncovering unobserved heterogeneity. Okay, this one sounds intriguing. Unobserved heterogeneity, what's the story here?
This is where it gets really interesting, I think. Imagine you're analyzing data from a large group of people, say, survey respondents. You run your model, get your average results for the whole group.
Standard practice.
Right. But what if, hidden within that big group, there are actually distinct subgroups? Maybe you have tech enthusiasts, budget shoppers, and brand loyalists, all mixed together, but you don't have labels for them beforehand. They're unobserved.
Okay, hidden segments within the data.
Exactly. Unobserved heterogeneity occurs when these hidden subgroups exist, and crucially, they lead to substantially different model estimates, meaning the relationships you're studying, like how price affects purchase intention, work very differently for each subgroup.
And if you just look at the average for everyone combined.
That's the danger. If you estimate just one model based on the whole data set when this kind of heterogeneity exists, you're bound to produce misleading results.
How so? Misleading in what way?
Well, think about it. Maybe a marketing campaign has a strong positive effect on the enthusiasts, but a strong negative effect on the budget shoppers. If you average those together across the whole sample.
They could cancel each other out.
Exactly. The overall effect might look weak or even zero. You'd conclude the campaign was ineffective when in reality it was having powerful but opposing effects on different important segments. You completely missed the real story.
That seems like a huge potential pitfall for marketing or policy decisions.
It really is. The good news is techniques for finding and dealing with this latent class techniques actually have a pretty long history in PLS. There's a method called finite mixture PLS, or FIMIX PLS, that's been around since the early 2000s.
FIMIX PLS?
Yeah.
Okay, so how does this work? How do you uncover these hidden voices?
There's a systematic, multi-method procedure that researchers often follow now, which combines several techniques for a more robust picture. It's like a detective using multiple tools to solve a case.
Okay, walk us through the steps.
Step 1 usually involves using FIMIX PLS for an initial assessment. The main goal here is simply to figure out, is heterogeneity likely an issue in my data at all?
Just first check.
Right. FIMIX PLS estimates models assuming different numbers of segments, maybe 1 segment, 2 segments, 3, and so on. And then it gives you a bunch of statistics called model selection criteria, or MSCs. These MSCs help you decide which number of segments fits your data best.
Okay, like guides to the right number of groups.
Exactly. There are several MSCs, and ideally you want them to agree. Two key ones are called AIC3 and CAIC. If they both point to, say, a three-segment solution, that's a strong signal. Others like AIC4 and BIC are also commonly used.
What are these criteria actually balancing? How do they decide?
Essentially, they balance model fit, how well the model explains the data, with model complexity, how many segments you're using. They penalize models that are too complex for the data, pushing you towards the simplest solution that still does a good job explaining things. Parsimony, we call it.
Makes sense. Are there other things to look at besides these AICs and BICs?
Yes, definitely. You also look at something called the entropy statistic, EN. High entropy, close to 1, means the segments are well separated, individuals are clearly assigned to one group or another. Low entropy means the segments are fuzzy, overlapping, maybe not truly distinct.
Okay, so clear separation is good.
Yes, and you absolutely need to check the segment sizes. Each segment you identify has to be large enough to be statistically meaningful. You can't draw reliable conclusions from a tiny segment of just a few people. There are rules of thumb for minimum segment sizes.
Right. Need enough data in each bucket.
Precisely. And there's another criterion called MDL5, which is known to be quite conservative, that often suggests fewer segments than might actually be there. So researchers usually consider it alongside the others, but don't rely on it solely.
Okay, so you look at all these clues. AICs, BIC, entropy, segment size. What's the verdict?
Well, if most of the reliable criteria point towards a one-segment solution, or if they give wildly conflicting results, making it impossible to settle on a number, then you might conclude that unobserved heterogeneity isn't a major issue. Your overall model is likely robust in this regard.
But what if they do point towards, say, 2 or 3 segments?
Then you proceed to the next steps, because you have evidence of heterogeneity. Step 2 often involves using a technique called PLS-POS, which stands for PLS Prediction-Oriented Segmentation.
PLS-POS, what does that do?
This method helps you dig deeper into the specific structure of those segments. It estimates the different model parameters, the path coefficients for each segment. So you can see exactly how the relationships differ between Group 1 and Group 2, for example. Maybe trust is super important for Group 1's purchase intent, but less so for Group 2.
So you get segment-specific results.
Exactly. But just knowing the segments exist and have different results isn't always enough. Step 3 is about explaining the heterogeneity.
Finding out why the groups are different.
Right. You want to understand what characteristics define these segments. Are they different based on age, income, gender, experience level, business size? You use techniques like contingency tables or something called C8 analysis to see which observable characteristics are associated with belonging to each segment. This helps you profile the groups.
So you can put a face on the segments, so to speak.
Precisely. And finally, step 4 is about formally testing the group differences. You use statistical tests, often a multi-group analysis combined with checks for measurement and variance, to confirm that the differences you observed in the path coefficients between the segments are statistically significant, not just random fluctuations.
Wow, that's quite a thorough process.
It is, but it's necessary if you want to properly account for this hidden diversity in your data. Researchers have used these approaches effectively. For example, finding different segments of consumers based on environmental attitudes affecting outdoor activity choices.
Useful for targeted marketing.
Definitely. Or finding different segments of national economies where competitiveness drivers work differently for tourism performance. Even segmenting restaurant operators based on how human capital affects their performance. It allows for much more nuanced and targeted strategies.
Okay, so understanding that your sample might not be one uniform blob, but potentially a mix of distinct groups, is vital for accurate conclusions. It really moves beyond those potentially misleading averages.
Absolutely.
Right, to bring all of this together now, the curves, the hidden corruptors, the multiple voices, let's look at that concrete example you mentioned from tourism research. Seeing it in practice should really help solidify these ideas.
Agreed. Let's look at the Amaro and Duarte study on online travel purchases.
5. Robustness in practice. The online travel purchase model. Okay, let's dive into this practical application. We're looking at a study by Amaro and Duarte from 2015, focusing on what drives consumers' intentions to purchase travel, online IPTO they call it. This sounds like a perfect case study to see our 3 robustness checks in action.
It is. They were quite thorough in testing their model.
So what was the basic model they were testing? What were they trying to explain?
Their main goal was to see how 2 key factors, trust in online travel vendors, and communicability, COMM, which is about how easily information is exchanged influence consumers' overall attitude, ATT, towards buying travel online.
Okay, trust and communication shape attitude.
Right. And then critically, how that attitude in turn influences the actual intention to purchase travels online, IPTO. They expected positive relationships all around.
Makes sense intuitively. How do they measure these things like trust and attitude?
They use standard survey methods. All the constructs were measured using reflective indicators, basically. Multiple survey questions designed to tap into each underlying concept, like trust or attitude. And respondents answered on typical 7-point Likert scales, from strongly disagree to strongly agree.
And who are the respondents? Where did the data come from?
They collected data via an online survey, getting 500 responses from people who said they regularly purchase trips online and use popular travel websites. Think Booking.com, TripAdvisor, Airbnb, those kinds of sites.
Okay, so experienced online travel buyers. Any key demographics?
Yes, and this is important context. The sample was primarily female, Malay, relatively young, mostly 21, 30 years old, and with moderate monthly incomes, roughly in the 420 to 840 euro range. So the findings are most applicable to that kind of demographic.
Got it. And they used standard software for the analysis?
Yep, they use Smart PLS-3, which is a very common software package specifically designed for PLS-SEM analysis.
Okay, context set. So how did the robustness checks play out? Let's start with their basic model assessment. Did it look okay initially?
Yes, their initial checks look pretty good. They assessed the measurement models first, checking reliability and validity. Things like Cronbach's alpha, composite reliability were fine. They also checked discriminant validity using the HTMT criterion. This ensures the constructs are genuinely distinct from each other.
So trust was trust, attitude was attitude. They weren't blurring together.
Exactly. The measures were solid. Then they looked at the structural model, the relationships between the constructs. Most of the hypothesized paths were statistically significant and positive.
Like attitude predicting purchase intention.
Right. Attitude, ATT, had a significant positive effect on purchase intention, IPTO, with a path coefficient beta of 0.419. Communicability, COMM, also had a significant positive direct effect on IPTO. Beta equals 0.279.
What about trust?
Interestingly, the direct effect of trust on IPTO was not significant. The beta was tiny, Naninger 0.015.
Huh. Trust doesn't directly impact intention to buy online travel. That seems counterintuitive.
It does at first glance. But importantly, trust did have a significant positive effect on attitude, ATT, with a beta of 0.251. And COMM also strongly influenced ATT, beta 0.443. So trust worked indirectly through attitude. More trust led to a better attitude, which then led to higher purchase intention. The total effect of trust was significant when you account for this mediation.
Ah, okay. So the initial model seemed plausible. But that non-significant direct effect of trust makes the robustness checks even more interesting. Did nonlinearity explain anything?
That's what they checked next, the nonlinear effects assessment. They used both Ramsey's reset test and the quadratic term approach.
Analytic curves?
Nope. The reset tests applied to the main parts of their model were not significant. P-values were well above 0.05. And when they added the quadratic terms directly, like trust predicting ATT or ATTAP predicting IPTO, none of those terms were significant either. Again, all P 0.05.
So pretty conclusive then.
Yes. Based on both tests consistently showing no evidence of nonlinearity, they concluded that their linear effects model was robust. For this group of consumers, the relationships between trust, communicability, attitude, and purchase intention were well represented by simple straight lines. No significant curves were hiding.
Okay, one check down. What about endogeneity? Was that lurking?
They moved on to the endogeneity assessment next, using that Holt et al. Procedure with the Gaussian copula.
Did they do the prerequisite check first? Non-normality.
They did. They confirmed that their key latent variable scores for ATT, COMM, and trust were indeed non-normally distributed, which meant the Gaussian copula approach was appropriate.
Good. And the detection step. Did copulas flag anything?
No, they didn't. They tested various potential endogeneity issues, for instance, whether ATT might be endogenous when predicting IPTO. In all cases, the Gaussian copula terms were not statistically significant. The p-values were all high, p is 0.751, p 0.81 p 0.302.
So no significant correlation between the predictors and the error terms.
Exactly. The conclusion was clear. Endogeneity was not present in this study. This was a really important finding because it meant they could be much more confident in the causal interpretations of their path coefficients. The relationships weren't likely being biased by omitted variables common to both predictors and outcomes.
Excellent. 2 checks passed. What about the last one? Unobserved heterogeneity. Were there hidden groups in their sample?
This was the unobserved heterogeneity assessment using FIMIC's PLS. First, they did a quick power check, which showed they had enough data, 500 responses, to potentially identify up to 5 segments if they existed.
Okay. And did FIMIC's PLS find multiple segments? What did those MSC criteria show?
This is where it got a bit ambiguous. The fit indices didn't give a single clear answer. AIC3 suggested a 5-segment solution might be best, but CAIC, AIC4, and DIC all pointed towards a simpler 2-segment solution. NDL5 also suggested 2, but remember, it tends to underestimate.
Conflicting signals. That makes it tricky.
It does. They noted it presented an ambiguous picture. However, they did look closer at the 2-segment solution. It showed decent segment separation. Entropy was high at 0.90, and both segments were large enough to be viable, about 80% in one, 20% in the other.
So 2 segments looked potentially plausible based on separation and size, but the main fit indices disagreed on the optimal number.
Exactly. Because of this ambiguity and the lack of a clear, consistent signal pointing to multiple distinct groups across the board, the researchers made a judgment call. They concluded that unobserved heterogeneity is not at a critical level.
Meaning they decided to stick with the results from the overall sample.
Yes. They essentially concluded that while there might be some minor variations, there wasn't strong enough evidence to suggest the presence of fundamentally different subgroups that would invalidate the findings from the total sample analysis. So the overall model was considered robust in this respect, too.
Okay, so putting it all together for this online travel example.
They went through the checks systematically: nonlinearity, no evidence; endogeneity, no evidence; unobserved heterogeneity; ambiguous signals, leading them to conclude it wasn't critical enough to warrant segmenting the data.
Which means they could be pretty confident in their original findings. That trust and communicability influence attitude, and attitude drives purchase intention. And these are mostly linear effects without major bias or hidden group differences for their sample.
Precisely. This example really showcases how these robustness checks work in practice. They didn't just build a model, they stress tested it. And because it passed these tests, their conclusions carry much more weight. It demonstrates the real value of going that extra mile to ensure your findings are dependable.
That's a great illustration. It moves the findings from just being results to being validated results.
Exactly.
Outro. So we've taken quite a journey today through the sometimes complex world of structural model robustness checks in PLS-SEM.
We certainly have.
We've unpacked why assuming straight lines isn't always safe, exploring nonlinear effects. We've demystified that tricky concept of endogeneity, the hidden corruptor. And we've looked into the subtle complexities of unobserved heterogeneity, the idea of hidden voices in our data. And I think it's become really clear that these aren't just, technical jargon for statisticians. They're absolutely essential guardians of reliable, trustworthy research. They help us get beyond those initial, maybe superficial findings.
That's exactly right. And knowledge, as we know, is most valuable when it's not only understood but also correctly applied. These methods, these checks, they're far from being just academic exercises you tick off a list.
Right. They have real consequences.
Huge consequences. They're crucial for ensuring that the conclusions you draw from research are valid, that they're reliable, and that they can actually be used to inform better decision-making, whether that's in business, healthcare, tourism, policy, you name it.
So it's about the confidence you can have when advising someone based on the data.
Precisely. And there's always more to learn, always refinements happening, embracing these robust methodologies, looking at things from multiple angles. It just enriches our understanding and pushes the boundaries of what we can confidently say we know.
And it does seem like the journey towards truly robust research is, well, ongoing. It's not like we've solved everything.
Not at all.
Even with all the advancements we've talked about today, our sources point to other areas researchers are still grappling with. Things like common method variance. What's that about?
That's another potential issue where the way you measure things, like using the same survey for all your variables, might itself create artificial correlations rather than the true relationships between the concepts. It's another layer of checking needed.
Okay, so the measurement method itself can be a problem. And they also mention things like differentiating between different types of models, or even being more certain about the direction of causality.
Right. refining how we confirm that A truly causes B and not the other way around, or that both are caused by C, the quest for certainty, or at least greater confidence, continues.
It really makes you wonder, doesn't it? With all these subtle influences potentially at play, curves, omitted variables, hidden groups, measurement issues, what other hidden factors might still be subtly shaping the facts we think we know right now?
Exactly. And that constant push for improvement, that critical lens, it underscores a core scientific principle.
Yeah.
Always question, always test, always seek to refine. There's always more to learn.
So for you, listening today, maybe the next time you come across a study or a report presenting some findings,
Perhaps you'll ask yourself, okay, beyond the headline result, how thoroughly were the foundations of this research actually tested? Did they check for curves? Did they consider endogeneity? Did they look for hidden groups? What might still be lurking beneath the surface that could change the whole story?
that's a great takeaway. Healthy skepticism and a demand for robustness.
Couldn't agree more.
Well, thank you for joining us on this deep dive into the crucial foundations of robust research using PLS-SEM. We hope it's given you some valuable tools and perspectives. Until next time, keep digging, keep questioning, and keep expanding your knowledge.